Hey everybody, welcome back. We want to again focus now on building our library of functions that we know how to differentiate and integrate. We're going to add from whatever we learned in a first semester calculus course, and we're going to start with exponential functions. And this will be our first type of function we want to investigate. And again, the big picture, right? What are the big issues in calculus? Differentiability, integrability, right? Those are two of the big players. And so we want to investigate what derivatives would look like for an exponential function and then antiderivatives as well. So let's go ahead and get started. All right, so exponential functions. Let's look at the function y equals 2 to the x. And let's look at this with the following restrictions. First, x is a positive integer. Well, let's think about this for a second. So 2 to the x. Let me just give myself some values here. 8, 9, 10. 1, -2, -3. All right, so if x is a positive integer, say 1, then 2 to the 1 would be what? 2, right? 2 squared would be 4. 2 cubed would be 8. Okay. 2 to the 4th would be 16, something way up there off my graph, just say. What about a negative integer? It's like 2 to the -1. Well, that would just be 1/2, right? So here, to the -2 would be like 1/4, 1/8, and so on. Now, what about rational? What if x is a rational number, like 2 to the 2/3, or 2 to the 4/5? Well, what's going to happen is we're going to start to fill in the pieces here to this function. Okay? But really, there's still gaps. You'll notice that positive integer, negative integer, rational. What's missing here? Well, what's missing is the case in which x is irrational. And why is that? Well, the reason why is this. We would like for this to be, what's the key word here? Continuous. That's right. We would like y equals 2 to the x to be continuous. And after all, what does continuity really mean? Well, it means that the limit as x goes to a of f of x is equal to f of a, right? That's continuity. And so here's the nice result. We can look at the function b to the x and call it the limit as r approaches x, b to the r, where r is rational and b is greater than 0. And so whatever x is, right, x could be the square root of 3. That's an irrational number. We can write it as this limit. We can find a sequence of rational numbers that converge to the square root of 3. And so that allows this b to the x to exist and satisfies what we need to have continuity, okay? So just to recap, this should all be reviewed, but these laws of exponents, we now have a continuous function, and we have these cases, right? If 0 is less than b is less than 1, f is decreasing, b is greater than 1, f is increasing. And furthermore, for all a, b greater than 0 and real numbers x and y, we have these rules. I'm not going to go through them one by one. They are very much review for you, but there they are. So let's think about the limits here as x approaches positive and negative infinity for the given restrictions on b. So for a, b is going to be something greater than 1. Well, when b is greater than 1, say, I don't know, 2 or 3, we have this. Okay. And so the end behavior, as x goes to negative infinity, well, this function is getting closer and closer to 0, right? So that limit is 0. Never actually reaches 0, but as a limit, approach 0. And similarly, as x approaches positive infinity, this thing just blows up to infinity, okay? Now, what if 0 is less than b is less than 1? Well, what happens here is that this thing really does that. That looks like a reflection over the y-axis. And think about it for a second. If I had, say, 1/2 to the x, I could think of that as 2 to the negative 1 to the x, which is 2 to the negative x, which is just a reflection of 2 to the x over the y-axis, okay? And so what will that do with these limits? Well, you can see that as x goes to negative infinity, the function blows up to positive infinity. And as x approaches positive infinity, the limit is 0, okay? All right, so here we go. What about the calculus, right? Because after all, that's really what we're after. What about the calculus? Well, let's consider b to the x. Let's find its derivative. So the derivative, we know by definition, is the limit as h approaches 0 of f of x plus h minus f of x all over h, which is the limit as h approaches 0, in this case, right, b to the x plus h minus b to the x all over h. And now I'm just going to do some algebra. So I've got a b to the x times b to the h minus, sorry guys, having some writing issues here. We have b to the x times b to the h minus b to the x all over h. And here we're just going to kind of follow our nose, see what happens. Hopefully you're looking at this and you're tempted to factor out b to the x, and that will be a good idea. That's b to the x, we'll have b to the h minus 1 all over h. And notice the limit is h approaching 0. It's not dependent on x. So I can actually bring b to the x out here. And we have b to the h minus 1 all over h. But notice that b to the h minus 1, right? This minus 1 is like b to the 0. So this limit here is really f prime of 0. Now this is interesting. This says that the derivative of an exponential function is just some scale factor of itself, right? F prime of 0 is a constant. And so this may seem somewhat dissatisfying right now, because what is f prime of 0? You kind of need to know f prime before you can find f prime of 0. But for now, we're going to just hold this. and come back to the f prime of 0 term as we proceed. Very interesting result. And I want to follow it up with this question. Is there an exponential function whose derivative at 0 is 1? Whose derivative at 0 is 1? Well, there is. There absolutely is. In fact, it's a very fascinating number with its own very rich history. It's actually Euler's number. E is the number such that the limit as h approaches 0 of e to the h minus 1 all over h equals 1. So that if we consider e to the x, so if I'm taking the derivative of e to the x, well, we know this is e to the x times, well, the derivative of e to the x evaluated at x equals 0, right? This is that f prime of 0 term. This is e to the x times 1, which is e to the x. So there is a function whose derivative is itself, and that function is e to the x. In other words, at any point on the graph of e to the x, the slope of the tangent is just whatever y value you're at. Very fascinating result. So let's use this fact, namely that the derivative of e to the x is e to the x. Let's use this along with some of the stuff we've learned in previous calculus courses or course to differentiate and integrate. So f of x equals 2 to the x. Well, this one's going to be a little bit unsatisfying, but I'm giving it to you now because I want to return to it later. At this point, all we know is this, okay? And so as unsatisfying as it may be, this is for later, okay? But it's a constant. That's what I want you to notice. It's a constant times 2 to the x. How about e to the 2x squared minus 1? Well, f is a composition. So we know that we're going to use the chain rule, okay? So f prime of x equals, well, e to the 2x squared minus 1 times, and then the derivative of 2x squared minus 1, which is 4x. So we have 4x e to the 2x squared minus 1, okay? If you want to think about u substitution, you could call u 2x squared minus 1, and so df dx would be df du times du dx, okay? So we just get this. How about e to the sine x? Well, my u is sine, so d du, or f prime, is just going to be e to the sine x times the derivative of sine x, which is cosine x. So we have cosine x times e to the sine x. If you want to write it like that, I don't really know why I rewrote it. It doesn't matter, but however you're comfortable. There we go. All right, how about some integration? So the integral of e to the x. In other words, what function's derivative is e to the x? Oh, well, e to the x. Well, e to the x plus a constant, okay? about B? Why don't you guys give this one a try on your own? You might pause the video and see what you get and then come back to it. So I'll give you a moment to pause. No, really, pause it. I hope you've paused it because I'm about to start. I'm sorry if this is getting annoying. Okay, so presumably you've paused and are back. So here, nice Calc 1 tool. I'm going to let u be x squared so that du is 2x dx. Also need to change my limits of integration. U of 0 is 0. U of 1 is 1. Yeah, it's the same values, but we've still changed the variable. This 0 and 1 are values of u, while the original 0 and 1 are values of x. And so this integral then will become the integral from 0 to 1. And notice that we have 2x dx, which is our du. And so e to the u du, which is equal to, well, integral of e to the u is just e to the u. We are evaluating from 0 to 1. And so we get e to the 1 minus e to the 0, better known as e minus 1. All right. And let's look at one more here. Secant squared x e to the tangent x. So again, you may notice we have a nice u substitution, nice review from Calc 1. So derivative of tangent, of course, is secant squared. Okay. And then, you know what, I apologize here. I want to actually quick style change my limits here. I meant to make this 0 to pi fourths. I apologize. Pi halves is no good because tangent's not defined there. And so we're going to have u of 0 is 0, and u of pi fourths is 1. And let's see what we get. So we've got integral from 0 to 1, and then there's my du, right? And so I'm just left with e to the u du, which again is e to the u, evaluated from 0 to 1. And what do you know? We get the same thing, e to the 1 minus e to the 0, which is e minus 1. All right. So that's exponential functions. I admit that it should be a little bit unsatisfying at this point because we talked about, I mentioned let's find the derivative of this new class of functions for us. And the derivative of b to the x is b to the x times f prime of 0. We need to know what f prime of 0 is. That's a problem. It's unsatisfying. I can't find f prime of 0 unless I know f prime, right? Or I can use the definition every time, and that's not all that efficient. So I admit that it's a little unsatisfying, but I want you to keep that at the forefront, right? That's what we're after right now. We're after the derivative of b to the x, a nice form for finding that derivative, really a formula. And so before we can figure out what that f prime of 0 looks like and give it some more specificity than just this random term, we need to actually look at log functions. Logs are going to play an interesting role in taking this derivative. And so that's where we're going to want to go next. And so in the meantime, I wish you happy studies and all sorts of fun learning. Until then.